Thank you very much for the introduction. The main aim of this study was to investigate and compare crack initiation and short crack growth mechanisms in different engineering alloys in very high cycle fatigue regime. From the literature, some of the main features of very high cycle fatigue crack initiation and early growth that have been reported are listed here. For instance, fisheye failure, which occurs around internal inclusion-induced fractures, and the different mechanisms for the formation of a rough area around the inclusions during very high cycle fatigue have been discussed by several research groups. For instance, the formation of fine granular area by Professor Sakai and optically dark area in which crack growth occurs due to hydrogen assistance as proposed by Professor Murakami, and formation of granular bright facets by Shiozawa. Fatigue crack initiation can also occur due to accumulation of localized slip, and also another important feature of the very high cycle fatigue failure is the location of fatigue crack initiation. Most of the studies have been focused on internal initiation, but there have been some studies which have shown fatigue crack nucleation from the surface as well. In order to fulfill the aim of this study, we have taken a variety of materials with different chemical compositions. For instance, high strength martensitic steel, the cold rolled duplex stainless steel grade, and then two hot rolled duplex stainless steel grades 2304 SRG and LDX 2101. Here, the amount of nitrogen plays a significant role in the damage accumulation mechanism that occur in these two grades. For the nickel-based superalloy Inconel 718, the main alloying elements are nickel 51%, chromium 19%, and niobium 5%. In the same way, the microstructure and the mechanical properties have a good variation among the tested materials. The high strength martensitic steel is 100% martensitic material. The cold rolled duplex stainless steel grade contained 60% austenite and 40% austenite. And the two hot rolled duplex stainless steel grades contain approximately 50-50 austenitic ferritic microstructure, while the nickel-based superalloy Inconel 718 is 100% austenitic material. In the same way, the mechanical properties of these grades have a good variation among themselves. For example, the tensile strength of high strength martensitic steel is the highest among this selected group, with the 2150 megapascal compared to the lowest being for 2304 SRG at 670 megapascal. The microstructure, all these microstructure pictures have been taken from the cross section of the specimen that was perpendicular to the loading direction. Here, for the martensitic steel, the microstructure is mainly consisting of martensitic needles. The specimens for this material were taken from the short transverse direction compared to the rolling direction. For the hot rolled duplex stainless steel grades 2304 SRG and LDX 2101, the microstructure was approximately the same, consisting of islands of austenite uniformly distributed in ferrite matrix. The grain size here is approximately 10 to 20 micrometers, and the specimens were also taken in the short transverse direction compared to the rolling direction. For the cold rolled duplex stainless steel, The microstructure consists of brighter phase here is the austenite and the darker phase is ferrite. The specimens were taken from the full thickness of cold rolled material of 1 millimeter along the rolling direction. For the Inconel 718 grade, unfortunately we can't show the pictures. However, the microstructure consisted of austenite and gamma prime and gamma double prime precipitates. In this study, mainly 20 kilohertz ultrasonic fatigue testing was conducted. The specimen designs for all the materials are shown here. For the high strength martensitic steel, Inconel 718 and hot rolled plate duplex stainless steel grades. The specimen design was hourglass shaped and cylindrical. For the cold rolled strip 1 millimeter thick duplex stainless steel specimens, we had to design the specimen together with the special fixtures in order for the whole assembly to have our natural frequency of 20 kilohertz. The materials were tested at different under different testing conditions. For the martensitic steel, the load ratio was R equal to 0.1 under air cooling. For Inconel 718, the load ratio was R equal to 0.8 under air cooling. For the hot rolled plate duplex stainless steel, the load ratio was R equal to -1, and in order to avoid excessive heating, we had to use water cooling. And for the cold rolled strip duplex stainless steel, the specimens were tested under load ratio R equal to -1 under air cooling as well. In the high strength martensitic steel, all the fatigue crack initiation occurred from internal inclusions. Here in this picture, one can see an overview of the fracture surface for this for this specimen that failed after 9.04 times 10 to the power 8 cycles at this stress level. Around the non-metallic crack initiating inclusion, one can see the formation of a rough area which resembles the fine granular area. Outside of the fine granular area, but within the fisheye, the fracture surface morphology is much smoother, but outside of the fisheye, the fracture surface morphology becomes rougher before the final failure takes place. It was easier to detect the fatigue striations within this region than within the fisheye. For the cold rolled strip duplex stainless steel, fatigue crack initiations occurred mainly at the surface defects. These surface defects were left over by cold rolling process and could not be removed during the polishing procedure without excessive thinning of these specimens. So this fracture surface is for a specimen that failed after 35 million load cycles at this load level. Even though the crack initiated from surface defect, but still one could see and detect the presence of fine granular area around the surface defect. In order to further investigate the presence of this fine granular area, we made use of focused ion beam milling technique to extract a lamella from the fine granular area. For this purpose, a platinum layer was deposited on the fracture surface, and the material surrounding was dug out, and then the lamella was extracted and polished using gallium ions for it to be viewed in the transmission electron microscope. Here on the right hand side, we can see the presence of a fine grained layer between the platinum layer, deposited platinum layer, and the bulk material. The structure of this fine grained layer is very much different from both the platinum layer and the bulk material. If we take a detailed look at this fine grained layer, we can see that it is composed of many fine grains of nanometric size. It was further indicated by the presence of diffraction fringes, which had different orientations in each of these small grains. In the hot-rolled plate duplex stainless steel, fatigue crack initiations always took place at the external surfaces of the specimens. Here we can see the crystallographic growth region for the LDX 2101 grade and the 2304 SRG specimens that failed after these many load cycles. Why we call the crystallographic growth region with this name is because we assume that the crack initiation has been taking place along favorable crystallographic planes in each grain, and at the grain boundaries the crack growth is hindered, and then it has to change its direction of propagation in the neighboring grains. So the mechanism of crack growth is crystallographic in nature for these materials. For the hot-rolled plate duplex stainless steel grades, fatigue crack initiation occurred due to accumulation of damage on the external surfaces of the specimens. For example, for the LEX 2101 grade, fatigue crack initiation, fatigue damage accumulation in the form of slip bands occurred in the mainly in the ferrite phase. There were some individual slip lines that could be observed in the austenite phase as well, but otherwise the austenite grains were virtually damage free. For the LEX 2101 grade, one could see that higher amount of nitrogen strengthens the austenite phase compared to the ferrite phase. Therefore, the damage is mainly accumulated in the ferrite phase. In comparison, for the 2304 SRG grade, the damage was mainly observed along the phase boundaries in the form of extrusions. And for this material, the balance of strength between the two phases means that the damage was accumulated mainly at the phase boundaries. In order to further investigate this damage accumulation, we took a failed specimen and cut it from starting from the fracture surface through the initiation point along the longitudinal direction of the specimen, and when we observed carefully near the external surface and the crack initiation point, we could see the presence of these persistent slip bands, which are mainly concentrated in the ferrite phase. This correlates with our observations of the external surface that I presented earlier. The slip bands are stopping at the austenite ferrite phase boundary, and they are approximately 45 degrees with respect to the loading direction of the specimen. In the nickel-based superalloy Inconel 718, fatigue crack initiation occurred at the grain boundary triple points. This could be seen by looking at the direction of fatigue striations within these grains. Here, after the crack is initiated, the crack propagation takes place along favorable crystallographic planes. So the crack growth here is also crystallographic in nature. So outside of this crystallographic growth region, the crack growth is less microstructure sensitive and becomes almost perpendicular to the loading direction before the final failure comes. Here we can see the size of FGA and crystallographic growth region that is plotted against the number of cycles to failure for each failed specimen. Here what we can see is that each data point corresponds to corresponds to the size of FGA and crystallographic growth region that was measured on the fracture surfaces of the faired specimens. What we can say is that the size of fine granular area is much smaller compared to the size of crystallographic growth region that was observed on the fracture surfaces. Also, the size of fine granular area increased for the high strength martensitic steel with the number of cycles that it took for the specimens to fail. In the same way, the crystallographic growth region for the hot rolled duplex stainless steel and Inconel 718 increased with the number of cycles to failure. However, the size of crystallographic growth region for the cold rolled strip duplex stainless steels did not show any variation with the fatigue life of those specimens. So, in order just to summarize, we have observed two different types of crack growth and fatigue crack initiation plus crack growth mechanism in our materials. Here, for both the crystallographic growth region and FGA were observed around crack initiations that occurred at the surface as well as internally. But the damage mechanism and the defect types that were responsible for the initiations were different in different materials, as I presented before. These are some of the conclusions from this study. I will not go through them individually, but I would like to thank the support of Sonic Materials Technology, Autocompo Stainless, and Udyog Home Survey. Thank you for your attention.